All right, press record. Welcome and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today we have the great pleasure of presenting a public lecture by Professor Laura Greene from the National High Magnetic Field Laboratory at Florida State University, entitled Exotic Superconductivity, the Dark Energy of Quantum Materials. Professor Greene is the chief scientist of the National High Magnetic Field Laboratory, or MagLab, and the Marie Craft Professor of Physics at Florida State University. She investigates electronic properties of strongly correlated quantum materials and focuses on planar tunneling into unconventional superconductors, including high-temperature superconductors, heavy fermions, and topological materials. She has held leadership roles in many scientific organizations, including President of the American Physical Society, Board of Directors of the American Association for the Advancement of Science, and is currently Vice President for Ethics and Outreach of the International Union of Pure and Applied Physics. Professor Greene was elected to membership in the National Academy of Sciences and also the American Academy of Arts and Sciences. She is a Fellow of the Institute of Physics in the UK, the American Association for the Advancement of Science, and the American Physical Society. Other honors include a Guggenheim Fellowship, E.O. Lawrence Award from the U.S. Department of Energy, Maria Goppert-Meyer Award from the American Physical Society, Belcourt Award of Excellence, Tallahassee Scientific Society Gold Medal, and 2024 Orsted Medal from the American Association of Physics Teachers. And she was appointed by President Biden to the President's Council of Advisors on Science and Technology, where she served from 2022 to 2025. If you have any questions during this talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Professor Greene.
Thank you very much, Dean. And it's a real pleasure. Share screen. It always takes me a second. Okay, you seeing the main slide there?
Yep.
Okay, thank you very much, Dean. It was a pleasure meeting you. We worked together on a committee not too long ago, and we really had fun on the committee and sharing some of our science. And if you ever get a chance to work on a committee with, I'm trying to get rid of this, but it's not working. If you ever get a chance to work on a committee with Dean, just say yes. So it's really a pleasure to be here. Thank you for the long and really too kind introduction. There's some of my bylines there. And here's a quick, as usual, there's always the challenge. No one's ever had a problem with the Zoom before. I have a great story about when I ran into a problem with the Zoom presenting to the president during COVID. But anyhow, PCAST plug, I have to say something about it, even though it's not the administration anymore. I'm going to tell you something about superconductivity. It's going to be very basic. But what I've learned through the years is that it doesn't hurt to get a little more basic. And I put my my email on there, and I love to involve, if people want to email me and ask questions, my only request is don't give up if I don't answer right away, because we're all overwhelmed with emails. I'd like to give you an introduction to the National Magnet Lab. Come and visit. I will host you if I'm in town and take you to Wakulla Springs. And also how great it is to just come and do experiments here and some of the things we're capable of doing. The next thing is I worked up a kind of a fun analogy a few years ago about dark energy and quantum materials. It's kind of a weak analogy. And I remind people by looking at that lower right picture there, and at the bottom, caution analogies ahead. Analogies help us in physics, okay? And for instance, my favorite analogy, the one we all love, is the Bohr model of the atom. And if you look too closely at it, it's wrong, okay? The next bullet is I'm not going to tell you about planar tunneling spectroscopy. I don't think we have the time, and it's a little too technical. But just like any astronomy lecture, I'll start out simple and blow you away with the last slide. Okay, so these are some pictures that I wasn't paid. In fact, it cost me money to be a part of it. We were paid, they paid us in bragging rights and pictures. And then the other thing that I'm still showing here is that everything disappeared off the web. We had 18. Can I move this out of the way? I guess I can. We had 18 total consensus reports and more products. And my highest contribution to PCAST was making sure every one of these reports had DOIs. So you don't need to look these up, but I did co-chair the one on AI and a few other ones, and the groundwater one I will mention during the course of the talk. But man, I learned a lot. And people say you did all these reports and they took all this time. To me, it was service to my country. And they're going to be out there somewhere. They're designed to be long lasting. Some of the PCAST Biden recommendations, like OTC hearing aids and the price of insulin, took years and years and years to come into practice. So I have hope that the work that we do will have some lasting benefit, and they're not filed away like all the DO reports. Oh, I'm sorry, I said that. Okay, so moving right along, I'm a low temperature physicist, and we've all seen high energy physics talks, and they're all required to show a picture of the collider from the distance, which doesn't mean anything. And I will say that I'm kind of required to show these pictures here in low temperature physics, and they kind of mean something. Over on the far right, we have a measure of resistance on the y-axis. I guess I'll just use my pointer, versus temperature. And what was completely surprised and took years to prove, we all know, well, I'll remind you that it's a function of temperature. As you lower the temperature, the resistance of a metal typically goes down. This is like boiling water. At high temperatures, it's hard for the electrons to go through. As you cool it down, the electrons go through more easily. So what was completely surprised and not predicted is that at a certain temperature, the resistance abruptly dropped. It turned out took years to prove it was zero temperature. It's easy to prove something small, but not zero. But they proved it, and they were also able to show that not only is there a critical temperature, but there's a critical current, and I'll mention again a critical magnetic field. In other words, if you put too much temperature, too much magnetic field, too much current, it stops superconducting. And those were some of the keys to understand what this was, because who ever heard of zero resistance? This is something, a lot has happened since 1911. And here's a plot of a small fraction of the superconductors. It's an old plot. I added a couple more superconductors on here. But what we have here is the y um, axis is the temperature below which, the critical temperature, the temperature below which the material is superconducting. Below that temperature, there's zero resistance. And the x-axis is what year they were discovered. So everything in red here is considered a conventional superconductor. And I will define conventional superconductors. We have a whole bunch of other things here that are not conventional. And that just means that we know a lot about them. We know they superconduct, but we don't know what the mechanism and why they actually superconduct. And I'll explain that what it means in a second. But I just want to remind you that all practical superconductors have to be very, very cold. So here we have boiling water, ice, and liquid air. And down here we have liquid helium. And so what we have here is that conventional superconductors are colder than liquid air. They're really, really cold. That's 77 degrees Fahrenheit, which is really, really cold. And but high temperature superconductors still have to be very, very cold. We can cool them other ways, and the other ways we can cool them are somewhat practical. We've all heard about this hydrogen-based superconductor that superconducts near room temperature. But in fact, it has to be done at such a high pressure, it's just not practical. So right now, anything practical has to be really, really cold. And to remind you what we mean by cold is if you've ever made pancakes, okay, which I did actually recently, what you need to do is make the griddle so hot that if you throw some water on it, it lasts, right? And so that's how cold you have to be. So what we have here on the far right, upper right here, is sticking my hand into liquid nitrogen. And it's kind what happens is that my hand is so hot compared to the liquid nitrogen that it evaporates the liquid nitrogen around my hand. The same way, the water gets evaporated very quickly, and so it doesn't get cold and it lasts for a while. This is really, really cold, and they're just some examples of things cooling. So I wish I had a demo, but let me just tell you that the temperature of superconductors compared to room temperature is even a bigger difference than we have between the frying pan and when we make pancakes. So there's a couple of things that define superconductivity. And the first one, as I mentioned, is zero electrical resistance. So in this kind of dark red figure, we have the resistance of a superconductor. Rho means resistivity. It's a kind of resistance. Lowering is a function of temperature. And below a certain temperature, the resistance goes to zero. Unlike a normal metal that never reaches zero resistance, it can get very low. The other thing that happened, which was a clear giveaway that it wasn't simply a perfect conductor, was this thing called perfect diamagnetism, or the Meissner effect. So I'm going to define both of those in the next couple of slides. And then I'm going to say something about that thing in the bottom is what do we mean by long-range quantum mechanical order? And this Meissner effect was a giveaway that that was the case. So first to tell you is that what does zero electrical resistance mean? It really means zero. It doesn't mean small. It doesn't mean little. It really means zero. So if you have zero electrical resistance, you have no power dissipation at all. So my example I like to use, which you use up there in Michigan, but we don't use in Florida, is a space heater. So we have two kinds of metals in the space heater. We have the cord going into the wall, which is a big floppy copper wire, and we have the high resistance coils within the space heater. If you plug the space heater into the wall and everything's working right, the coils get hot and glowy and nothing happens to the copper. Why? The copper has very little resistance. The electrons flow very freely. When they go into the heater wire, they have a hard time and they're wrestling, pushing to get through. And that resistance is like a friction. So just like when you rub your hands and they get hot, these get hot. It's the same kind of thing. And there's a lot of power dissipation. That's resistive loss. And we lose billions of dollars a year in our electrical power grid in the United States. If we can put in certain places with superconductors, we'd save a lot. Now, going back to our subject here, a superconductor literally has zero resistance. So zero power dissipation. If I had a battery here in Florida and you had a light bulb up there in Michigan and we connected them with superconducting wires, it would light up, nothing lost. It's hard to understand. So that's zero electrical resistance. And what does perfect diamagnetism mean? That means magnetic field is expelled. Now, I'd like to spend a little time and talking the difference between perfect diamagnetism and a perfect metal, but I don't really have the time. I'd love to talk about it, but just to let you know, and I have a little tiny video, which you may have seen before, that says no matter which way, the superconductor just pushes away the magnetic field. And it does it because it has zero electrical resistance with its electrons that are superconducting. So no matter how you put it in the field, the electrons move around to expel the field. So I hope that's a beginning explanation, but just to show you how they work, here's a picture which you may have all seen before of the bottom down here is a superconductor at high temperature superconductor at liquid nitrogen temperature. And this is one of those strong magnets that just bounces away, and it's quite stable. In fact, it's more stable than balancing magnets. Harshaw's theorem dictates that you can't balance magnets, that it's an unstable equilibrium. Because of something that I'll show you, I'll give you another slide and then a very funny video. We actually have, in certain kinds of superconductors, they don't expel all of the magnetism. Some of the magnetic field lines get stuck and make it stable. And so that's why these are very possible to make things like levitated trains and make them stable. I have a picture here on the right of a prototype high temperature superconducting magnetic levitated train. The one in Shanghai, the levitated train in Shanghai, is not superconducting. This one is not only superconducting, but it's high temperature superconducting. The Japanese have actually had a levitated superconducting train since the 60s. They use conventional superconductors. And I don't have a picture on the slide here, but my Japanese friends all told me that it only went about 1 kilometer, which was just long enough to take their funding agents for a ride. So how do these things work? So I have one simple slide here, and it's not to have you understand what, the microscopic properties of a superconductor, but this does explain the microscopic mechanism only for those conventional superconductors, the ones that we showed in red in that funny slide with all those dots as a fun, TC versus time. So the problem was that some of you probably already know that bosons can go into a single quantum mechanical state. So that's like photons, phonons, anything that's a boson. Mr. Fermi taught us that no, Fermi and Dirac told us no, fermions are just not party animals like bosons, and they don't like to go into the same quantum mechanical state. And in fact, Mr. Pauli said, no, 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 you cannot do that. And one of the things I love about quantum mechanics is things that don't seem reasonable are. So you would think you should be able to squash these fermions together and make a single state and have it flow without any loss or anything like that. But in fact, they don't do it. So this was solved in 1957 by Bardeen, Cooper, and Schrieffer at University of Illinois. And not only was the Fermi-Dirac statistics say you can't stay in the same superconducting state, but so you want to pair them up somehow. So you have 2 1/2 electrons. How do you pair them up to get, act like a boson with spin 0 or spin 1? Not only are they not supposed to do that, but they all have a charge of -1 electron. So how do you repeal Coulomb's law? So this was this clever thing it's not the electrons that are electron-electron pairing, it's the background, it's the lattice. So this is a very old analogy. And if you look at the bottom, the soft mattress analogy, you have 2 people that may not even like each other. And they're on a really soft, squishy mattress. And if they lay down on the bed, they're stuck together. And then you could argue that, well, if they really don't like each other and one of them jumps, holds onto the bed and then finally climbs out, and then the other one, slowly the mattress may lighten up, and that will give you the strength of how much they're paired. And as they're coming out, it gives you the time involved. This is an analogy. Don't push it too hard. The another analogy is up here. So above a certain temperature, everything's bouncing around and the electrons are bouncing around. You go below a certain temperature and the whole background, the lattice or phonons slow down and they're not as violent. And if you have a material with a strong electron lattice, a strong electron phonon interaction, when the electron goes through here, as long as it's below a certain thermal temperature, it can draw in the lattice. And what it does then is it leaves a positive wake, like the wake of a ship. And then another electron sees, oh, this is all positively charged here. I want to go there. Okay, so that is a very general gut explanation that holds pretty well. And this explains all of the conventional superconductors, all of them. In fact, that's the definition of a conventional superconductor if this theory holds. And I will also add that we have many other mechanisms for superconductivity, these exotic superconductors. And in the high temperature cuprates, not only do we think there is a very important electron spin interaction, but it looks like this also plays a role. So this is all very important. I'm going to add one more thing that I will repeat more than once, which is that there are many, many, many kinds of correlated electron. This is a correlated electron problem, and I'll define what that means again. It means that it's not a Fermi liquid, and I'll tell you what that means. But what I will tell you is that even though we understand, and I'll say it again in a minute, We understand how copper works. We understand how silicon works. We understand how a superconductor above its TC for most materials work. But when we go into some of these exotic materials, we don't understand them. There's some weird electron-electron correlations that we can't model. So now that I've confused you, let me talk again about superconductors just to go to a fun analogy here, a fun slide. I mentioned before that some superconductors actually have some of the magnetic field gets pinned inside of them. You don't need to know there's two kinds of people, there's two kinds of superconductors, there's two kinds, In any case, all practical superconductors are type 2. That means they can take a much higher magnetic field. Anything, whether it's a levitated train or an MRI magnet or whatever, they can take higher magnetic fields. And if you have these magnetic fields penetrate, they make these vortices, and you can pin the vortices by putting defects. And you have to remember, if you want these to be practical, you have to pin the vortices because inside of this vortex, the blue part is superconducting. Inside of this vortex is not superconducting. So if these vortices move, you have non-superconducting electrons and you're going to dissipate energy. So part of the applications research is how do we pin the vortices? Now for the fun part. Let me know if you don't hear the audio. Oops. Okay. So the word engage is these kind of things are just meant to engage the general public and to look things up or ask me. So what we do want to do is the need for new and better superconductors. And the niche, and I'm not going to, all these talks on practical superconductors, but we do need better ones. If you want to make a very, very large magnetic field, like we do with the Magnet Lab, you need to use high TC. If you want to detect very small magnetic fields, or like in quantum computing, you need superconductivity. In energy, as I mentioned before about the grid, if you want to transmit, store, or generate power, superconductors are ideal. And so the research goes on. Nobody knows how to design a superconductor, not even a conventional superconductor, but we're all trying. Predictive design of materials, ha ha ha, but we're working on it. And by the way, we can predictively design hard materials, all kinds of things, semiconductors, but the strongly correlated materials like a superconductor or thermoelectric, all bets are on. These are, in my opinion, the most fundamental problems in all of physics, but that's the way I feel. So now I want to go on to the Magnet Lab, and it's been around since 1990, and basically it's a user facility with big magnets. Come and visit. I find in public lectures, I have to remind people that just like there's two types of superconductors, there's two types of magnets. There's the kind that you can dig for and go onto your fridge, and those are just regular permanent magnets. And then electromagnets, many of you have probably done these where you wind a wire around a nail and you stick it onto a battery. And these are electromagnets. And what we use at the Magnet Lab are the electromagnets. It's a combination of both resistive and superconducting electromagnets. Now, the National High Magnetic Field Laboratory is a big thing, and I want to just give you a big overview. Here is our facility in Tallahassee. That's what the building looks like. When I walk between my office and my lab a few times a day, my Apple Watch says, "Good job." We're home of the highest DC magnetic field in the world that actually produces data, and it's a 45 Tesla hybrid magnet. By the way, to tell you what 45 Tesla mean, your refrigerator magnet is about 0.01 Tesla. And if you go to a junkyard and you see one of these electromagnets that pick up cars, that's 1 Tesla. So this is really, really big. When you go into an MRI, it's 1.5 Tesla unless you're especially placed. So these are really, really big fields. Speaking of MRI, we have this thing here that's a 21 Tesla MRI magnet that we can do functional MRI in. It's a monster of a magnet, and come and visit and see it. It's amazing. I will show a couple of science highlights. At University of Florida, by the way, we have 7 user facilities in Tallahassee. I'm not going to list them all. We have 2 at University of Florida. What we have is the highest B over T, so we can go to 17 Tesla to half a degree millikelvin. And we also do this advanced magnetic imaging and resonance spectroscopy again, I'm talking too fast, sorry, again to 21 Tesla. And we can do human imaging up to about 17 Tesla. And not only do we do work in a lot of materials, but we also do work with health facilities and research on humans. Then we have at Los Alamos as the pulse field facility. This is a regular size human, and this is the generator that's being fixed right now. And there you can get 101 pulse, 101 Tesla pulse, and it's useful data. It's an amazing facility, and I've known about this. I was going to use this same facility when I was doing fusion research in the 70s. So now it's being used for the pulse facility in the magnet lab. We host every year over 2,000 users from 200 institutions across the US and over 300 institutions internationally. We train lots and lots of people. This is my slide to say, National Science Foundation, it's great that you support this. It's good for national science and international science. And I want to stress that newcomers are welcome. Every year, at least 25% of the principal investigators are first-time MagLab users. Google MagLab, Google whatever you want to do. It's a very short proposal. Look for the scientists that will help you write it. We want to bring people in. The scientists are very helpful. It's free to use. You just have to get here. And I have a big house, especially during a football weekend. You can come and stay with me. So this is one of our R&D awards. It's a 32 Tesla all superconducting magnet. It was the largest all superconducting magnet in the world. It was a user facility. Unfortunately, it's being fixed right now, but when you're always pushing it forward like the 101T, you do a lot of that. I'm going to do just a few minutes. Well, it's only 1:30. A few minutes of just some science highlights, just to inspire you to think about things that you can do in science. Again, I'm not trying to train you in physics here. This is more of a TED Talks where you walk away and you think, oh, I feel good about this. And so I'm not training you. This is to publicly engage you in what you think might be interesting. Our main themes are materials, energy, and life. So I'm going to give just a couple of materials examples. I can give a lot more, but this is one that was a few years ago already. But what we have here is something called a heavy fermion superconductor. Fermion is an electron is a fermion. And all I want to tell you right now is that I've been studying these most of my adult life. And if you measure the mass of an electron in a heavy fermion metal, the mass of the electron is 100 times to 1,000 times the free electron mass. You cannot get that by understanding how the electrons work within a lattice. It just doesn't make sense. So normally in Fermi liquids, if you know what the lattice looks like, and you know what makes up the lattice, I'm going to repeat this a couple of times. If you know what's in the lattice, you know its crystal structure and what's in there, you can tell what the transport properties are, what the thermodynamic properties are, what the optical properties are. If you have electron-electron correlation, all bets are off. If you calculate what the mass of the electron should be in this material, you'd get basically the mass of electron, not 100 times the mass of the electron. So it's some weird electron-electron interaction that we're still understanding, and it's really fun. Okay, so what do we have here? What we have here is that, remember I told you that as a function of field, you can kill the superconductivity. So what we have here on the y-axis is the magnetic field. So this goes up to a little over 60 Tesla. So we use both the DC facility and the pulse field facility. Here is an interesting axis. It's an angle, okay? So this is an angle of which the magnetic field is applied. And we see in the blue area, below this blue area is where it's superconducting. As you would expect, if you go above a certain field, the white area is where it's not superconducting. If you go to this zero, who cares about what zero means in this? Zero angle, this thing superconducts all the way up to 35 Tesla, which is very surprising. What's more surprising, and then if you apply a higher field, you force these electrons to be a magnet, because the magnetic field said, you just follow me and don't listen to me. So this started a whole new field. And what they found is that at certain angles, as you raise the field, you kill the superconductivity, and then it starts superconducting again. And it's definitely weird, and it's talked about all the time, and it's not understood why. Plus the fact this kind of superconductivity looks like it's a really lasting, robust superconductivity, which we call triplet, who cares what that means? Topological. To me, topological, and what it should just mean to you is that topological just means protected. It's really hard to kill it. So this is a little bit elusive up here, but it's very, very promising. If it's really a topological superconductor, it has a chance to being used in sensors. And of course, what we put in all of our proposals to get funded. Are you ready? Quantum computing. Okay, moving along. Here's one that I like to show off, and that Fabiola Giannotti, who's the Director General of Fermilab, loves the Magnet Lab. And she is on record many, many times of saying that what's limiting the colliders is the strength and the quality of the superconductors. And let me just tell you that we work a lot with them. We've developed, we have actually they're using new kinds of superconductors based on a lot of the Magnet Lab research to use a better superconductor that's harder to use in these colliders. And in the future of the future collider, we invented a material that's this kind of material that's alloyed, that is actually a prospect for the next future circular collider. And it's not just the MagLab Applied Superconductivity in our Magnet Science and Technology Centers. We also work with Lawrence Berkeley Labs, Brookhaven, and now Argonne. So it's a universal effort. These energy examples are really cool. I didn't know about a lot of this before I came to the Magnet Lab. We have something called ion cyclotron resonance. And just like you would expect, it's got cyclotron and resonance going on there. So we do this as high as 21 Tesla. And basically what you do, it's a mass spectrometer on the strongest steroids that have ever existed. So what you do is, it was developed for the most complex organic fluid on the planet, which is petroleum. And it's really great. We have all these scientists in the Magnet Lab that worked in the West Texas fields, oil fields, and they actually, it's fun to talk with them. They're great scientists. So what you do is you spit a little oil or whatever your complex fluid is, and you separate the masses with the high field, and then you chirp it. And what we see here is a really complex spectroscopy. So the y-axis is not just the amount, it's a little more complicated than that. But what we see on the x-axis here is the mass. And so we see next to ion cyclotron resonance, quantum time of flight was the primary competing technique, and that's this resolution. In ICR, ion cyclotron resonance, you have this kind of resolution. And what's extraordinary to me is it can give you mass resolution of 1 electron. So let me just give you a couple of examples. It was invented for petroleomics. For example, did BP and Exxon strike the same reserve in the Gulf? Since it costs more than $1 billion now to dig a well, they want to know, and we can tell from the fingerprint exactly if it's the same reserve or not. Another thing is forensics. If we know the Exxon Valdez did the spill, they don't ask us. But decades after a spill, we can tell you exactly where the oil had originated. Proteomics, is another area that we look at. And one example is, if anybody here knows any biochemistry, everybody's favorite protein is something called P53. As many of you probably know, is the way a protein folds determines its functionality. And the P53 registration can be anything from perfectly healthy to neoplastic to malignant. And we can tell exactly how it folds by doing an hydrogen deuterium difference and tell you exactly how it folds. So it tells you a lot of protein makeups. This is a little too complex for me in the details, but what I will tell you about now is how it's used a lot for climate change and sustainability. Just to show you some pictures, we do have scientists that go up to the Great Rivers Observatory all over the Arctic and just take samples. And there's 6 rivers, 6 years, 6 samples per year. They track how carbon is getting into, and the kinds of carbon are getting into the water. And we also do work on groundwater that tells you exactly what's in the groundwater, which was not only the Arctic, but all over, which was a little more politically charged than I ever expected when I worked on the groundwater report for PCAS. Over here is something that it's another example where that's the mass of an electron. Here's another one of these spectra. And what we have here is that the runoff in the built planet creates all these asphaltenes. And they look almost identical. They can have an island shape or an archipelago shape. And it turns out some of these shapes are water insoluble. Those are the good guys. If they're water insoluble, they will not go into the groundwater. And you might be able to mine them to use the carbon for other products. If it goes into this kind of archipelago shape, it can be soluble. The dissolved organic matter is dissolved in the water and then can leak into the groundwater. And that's very dangerous. We would like to put constraints on this, but again, it's hard to put regulations on things. Finally, I just want to point out that we do a lot of work on PFAS, which are these forever chemicals. And it turns out that the EPA can test for a few of them. We can test for hundreds and hundreds of thousands of them. And the other thing that we found out, which is a fairly recent, not that recent of a study, was we did work on the plastics that are supposed to last forever, whether it's a test or a Kmart bag, and they're not forever chemicals. They break down. So it would be interesting to follow, the cradle to tomb, what's going on and what we're putting in the planet. This is a fascinating area of research. Now for the health directions is I mentioned commercial is now typically 1.5 Tesla. We can do 21 Tesla. So what in MRI, you have a resonance between the field that you put on it and what you're doing is you're doing a spectroscopy with RF light, okay, like radio waves. So if you're at 2 Tesla or 20 Tesla, you have 10 times more resolution because you have to use 10 times shorter wavelengths to do the imaging. So this is what we used to have. You could do a single cell at a millimeter. Now we can go to microns. So that's the big resolution change. And what we can do, one of the things we do a lot of study in Florida is early detection of plaque amyloids. It turns out, again, this is all research, that plaque amyloids, when they form in the brain, they create tiny microhemorrhages. Microhemorrhages are water, it's blood pooling. And so the advantage of doing this at 21 Tesla is that you can define, if you get a hemorrhage, you can detect it at micron size, not millimeter size. So it will tell you if you have tiny, tiny hemorrhages in the brain. Oops, sorry. This is my favorite, and it's a little bit older of a research, but I think this will be my last, this is my last example, which is not only, we have tons of examples at 21 Tesla, you don't just have to image water. You don't just have to image the blood. You can look at anything. On the left side, what we have is the image of a rat brain, and I found out you can buy a rat with brain cancer, a living mouse imaged at 21 Tesla, but we're not imaging water, we're imaging sodium. Why do you want to image sodium? As cells are dying, they uptake sodium. So we have here on the left the image of sodium. It's lower resolution. Sodium is a lot heavier than a proton, but you can chemically identify the sodium. You give the rat chemotherapy, an image 4 days later, and you can repeat this. If that image lights up, which means it's uptaking sodium, that gives you some idea that this indication that this chemotherapy might actually be working. And if we could expand this to human size, this would be fantastic. But it'd be great early detection of the quality of chemotherapy. I'll skip this one. Okay, so like I said, I'm going to give you a couple of analogies. Can I have 5 minutes?
Mhm.
Okay, yeah, thank you, Dean. Everybody, if you go to sleep, if anybody doesn't want that, put in the chat like quiet, Laura. Okay, so what I said before, why do I call this dark energy of quantum materials? It's because I kind of liked the title. And it's because it's just really unsolved. And I wanted to ride the gravity wave when that came out. And just to remind you, there's a lot of unification across physics. The details, the devil's all in the details. But just to remind you that there are many of the mathematics that we use for the inside of neutron stars and for superconductors. And a lot of the mathematical uh, techniques that we use for what I have here are the same. These aren't the same, but it just reminds us the unification of something across physics. And so black holes were across the entire universe. Quantum materials have these correlations on the order of 10 to the minus 10 meters. But they do have a lot in common and a lot different, but it's kind of a fun to think about that. I don't think I'll talk too much about the heavy fermions. I mentioned that. I showed you this plot once before, and now I'm going to tell you exactly how I characterize something that's not in the red zone, not a conventional superconductor. And that's by this picture here. And this picture here is a phase diagram. Blowing it up here, what we have here is the y-axis is temperature. The x-axis is a thermodynamic variable. It could be pressure. It could be changing the number of carriers or doping. And this is true for like 50 classes of unconventional superconductors. Not true in the case of a conventional superconductor. A conventional superconductor is a conventional metal above Tc and then a superconductor. It just doesn't have this. What we have in these unconventional superconductors at high pressure or at high doping, it's a simple metal like copper. At low pressure or low doping, it's kind of acts like chemically like an insulator or a really terrible metal. Where these things meet, they create a superconductor. Still under study, but it happens like all the time. What we have here above this dome here is things that, we could model a simple metal, we could model certain insulators. Up here, we have many complex phases that are yet unsolved. I will say in the last year, one of them seems to be solved with something called the Planckian. Anyhow, we can talk about that another time. And this is just a general thing to show ubiquitous. Okay, there's at least 50 families of unconventional superconductors. And one thing I've been saying for the last 30 years or so is that they cannot all have the same mechanism. But underneath the dome, all these domes here, all of these domes, okay, here's an organic, here's the cuprates. So don't worry about the details, but under their domes, they're all Cooper paired. Okay, they're all Cooper paired. We don't know why they're Cooper paired, but we can model it. Just like we can model what's going on in the normal metal or the Fermi liquid, we can say these are Cooper paired, and instead of having the Schrodinger equation, which is the basis of Fermi liquid, of applying that correctly, we have something called the Bugoli-Bove-Dejean equations, and we can model all that stuff. Okay, so let me go on to the next picture, which is just looking at the dome, okay? All high TC superconductors are unconventional. Some low TC ones are also. All unconventional superconductors have these weird states of matter which we cannot explain. In fact, I'll make a general statement of that. It breaks the symmetry of the underlying lattice. Now, I like to point out that this is a dome. So TC goes down here, and TC goes down here, and it's higher in the center. It's clear that too little correlations or too many correlations drive down TC or take from the Cooper channel. You need some of these weird correlations to get high TC, and we don't know the balance. Now I'm going to end with a couple more slides, and I promise to finish this quickly. But some of these, let's just talk about one. One thing that we have above, this is my data, above TC are some weird things that happen, like the electrons bounce into things called nematicity. The name is terrible. It just means they go into cigars or little things like this, and we can't explain that. There's some kind of electron-electron correlation that before it goes superconducting, the electrons line up in ways we don't really understand. What we've been able to do in the last 20 years and even longer is develop many, many new techniques to study these things. And this is just to, again, I'm going to blast you with the last slide, just to show you that there are so many techniques that my poor students that we spend every summer studying what these techniques and what they actually measure and putting it together. So this is something called quantum oscillations we do at the Magnet Lab that tells you how the electrons move in orbits in high fields. We have things like scanning tunneling microscopy that tells you locally how the electrons behave. I do planar tunneling spectroscopy. Besides the techniques, some of the experiments I've done just in the last few years were not possible, but the people that are the best in the world at growing the materials have made better materials. These are hard materials to grow. Finally, the computational techniques are blowing me out of the water. I don't do that, but a combination of measurement, growth, and computation techniques are really improving our knowledge and understanding. So now I'm going to do the analogy. I'm sorry I'm going too long. So what's solved quantum matter are Fermi liquids, superconductors above TC, and superconductors, we know we can model them. And the general definition for an unsolved quantum material is that it can't be described by the crystal structure and the atoms that are in the crystal, and the electron-electron interaction is stronger than can be calculated. You get funny things when you measure it. So now for some pictures. Conventional superconductor. Above TC, it's a simple metal. Below TC, you have that kind of Cooper pairing that I showed you. These are some of the few really solved problems. They're really solved. It's very cool. Unconventional superconductors. Up here, we have a conventional a conventional metal. Under the dome, we have Cooper pairs. We don't know exactly why they're paired, but we have Cooper pairs. And then all this area up here are things that we just don't understand. Now the analogy part. I had the lucky part to be on the Kavli committee one year, and when Weiss, Barish, and Thorne got the award for LIGO, they then got on to get the 2017 Nobel Prize in Physics. I saw this picture here, and Kip Thorne gave an amazing lecture. They all give amazing lectures. I saw this picture and I thought, oh, what we have here is a background distortion of the space-time continuum due to the mass of a star. And this is being drawn to it, this planet or something, due to a distortion of the space-time continuum. Does that look like BCS, electron phonon superconductivity? So I talked to my friends at the Kavli meeting in Oslo, and they decided I was certifiably insane. Yeah, probably am. But I had about 45 hours to get the analogy. So it's weak, but here we go here. In gravity, Einstein was able to show that it didn't work. Newton didn't work all the time, right? It worked. It worked a lot. He wasn't wrong. But there were a few problems, like the retrogression of the perihelion of Mercury. And he just said, oh, and he found a microscopic explanation. It's a little bit different, but Bardeen, Cooper, and Schrieffer knew that superconductors weren't like copper, and they found something that they could explain. Doesn't explain everything, but explains a lot. Two more slides, and I don't have to talk about my own work. Um, LIGO was amazing. Two black holes colliding was more than the combined power of all light radiated by all the stars in the observable universe. But it's not light, it's gravity waves. Okay? This is a fundamentally new detector. In quantum materials, as I mentioned, we have a host of growth, measurement, and computation techniques that give us this complicated scope. Okay, so all I'm trying to say here is that for the first time ever, we have a way to measure the universe that's not light or matter. Will this be a key to helping us understand these fundamental problems? What is dark energy and what is dark matter? And I have the same thing here. Will all these help us understand all these quantum matter detectors and what's going on in these many, many questions? And I'm not going to go over this. This is my material du jour, which I was going to mention. This is obviously not a Fermi liquid, resistance versus temperature. One slide of data that is very cool that says, I'm happy to talk about this another time. I'm doing a lot of talks on this also, is that if you put this superconductor in a magnetic field and you measure, this is its electronic properties by tunneling, you kill the superconductivity and a whole new gap feature appears when it's not superconducting anymore. The only way we can explain this is that the electrons are pairing due to it's cerium, cobalt, indium 5, due to scattering off of the cerium atoms. Okay, now you can go away, feel like you hopefully feel better about this stuff. There's a lot of good reports out there. There are many, many unsolved problems in quantum materials, and it's just really hard. Many of my friends have left this field because cold atoms, at least you can calculate. Finally, come visit the Magnet Lab and be in touch. Thank you very much for your time.
Thank you so much, Professor Greene.
Oh, that's cool.
That was an inspiring lecture. It was well explained and it was beautifully executed. So thanks so much. There must be questions. So go ahead and type into the chat or the question answer dialog box. But while we're waiting, maybe I can ask a question. Of the unconventional superconductors, which ones are seeing the most practical use these days or potentially future use?
The cuprates.
The companies.
So things like yttrium, barium, copper oxide, actually they're called REBCO because they use other rare earths. And those have the most practical applications, not because the TC is so high, because they can take so much current and field. If you want to make a 32 Tesla
Mhm.
high field magnet, you have to use high TC.
Mhm.
And in fact, one of the interesting things is that the Magnet Lab was the biggest purchaser of these Repco tapes in the United States. All of a sudden, a few years ago, they can't keep up with it. It's because the fusion people are now buying all these tapes. And it was the Magnet Lab over decades of federal funding that have been working with the distributors, the providers of these tapes that have made the quality so good that we're in good running for probably to a possible fusion reactor,
Mhm.
which you need high TC for.
I see. That's great. And in terms of also the unconventional superconductors, some are 2D and some are 3D. Can you talk a little bit about which ones are 2D, which ones are 3D, and if there are any differences?
Yeah, but one of the general things that we kind of learn, I'm not going to show the crystal structure. Maybe I'll just take off the
Mhm.
stop sharing. So it turns out the highest TC materials are all pretty 2D.
Mhm.
So things like the bismuth materials they're so 2D that the planes don't even talk to each other. The cuprates are also. So it seems that the highest TC materials are 2D. When you go down, they're all somewhat layered. So they're all somewhat layered, even in things like the ones that I mentioned are being used in colliders now, like niobium 310. It's more 3D, but has a little bit of a layered structure. And Zach Fiske used to always say superconductivity runs through crystal structures. And so there are some correlations. So one of the things that people have looked at is, can you separate the planes, make them more 2D?
Mhm.
And but that's sort of the general.
Okay. There's a question, the question from Mark Dickman. He writes, "Thank you for the wonderful talk. Could you please tell more about your research? The gap opening is very interesting. What is the symmetry of the Cooper pairs in this compound?"
Okay, I don't want to waste everybody's time here, but okay, but I mentioned this material. I'm not sharing, of course, so I'm doing everything wrong. That's what we do. So this material is a dx squared minus y squared or d-wave superconductor. And we actually proved that by this measurement here a long time ago with using something called point contact spectroscopy, which is related to tunneling spectroscopy. Tunneling is better, and so we did a lot of work to increase the quality of tunneling into this material. And I'm not going to go, oh man, where are the slides for this one? Sorry. Okay, I'll do this here. So that's how you tunnel. Whoops, wrong way. So this slide here is this is the planar tunneling. And let's just look at these two orientations. This one is going down from the z-axis, and this one is coming in from the side. And what we see is if you have a conventional superconductor, you can see this gap-like stuff. We have lots of data. This is just stuff I pulled up right now. As you raise the temperature, it gets flat, but not in these materials, not in any of the unconventional superconductors. When you go above TC, you see all the structure. I'm going to make one statement, which I'd be happy to discuss another time. One of the strengths of planar tunneling above STM and other measurements is that it specifically picks up non-Fermi liquid behavior. So if it's non-Fermi liquid, we see structure.
Mhm.
So we have a color plot here, not just to get it published in a high impact journal, but just to show that this is temperature up here and this is voltage across here. The dotted line is TC. Above TC, we see stuff here. After we did this, the STM people also see it, and we're all in agreement on that. The interesting thing is the magnetic field behavior. So these two measurements are taken at low temperature, 40 millik and 20 millik. I'm sorry, 0.4 and 20 millik, and they're done at high field. So we're at very low temperature. We see the gap in the z-axis direction. As we raise the field, HC2 is the field above which it's no longer superconducting. HC2 is 5 Tesla. Here we are at 6, 9, 11, and 14 Tesla. There is no superconductivity in here. Okay. Here, if we go in the A-axis direction, 100 direction, here's the gap structure. We're down at 20 millik. We raise the field. Okay. HC2 is 12 Tesla. And here we are at 14 and 18 Tesla. There's no superconductivity there. Okay, more taking data here. These are the data that I showed you. Now, remember when I told you there was something going on a little bit above TC?
Mhm.
These are tunneling spectra as a function of applied field in that region where it's not superconducting, but not too high. That region is TC, which is about 2.3 and about 5 degrees. Okay. And what we see that in that pseudo gap region, which we think is preformed pairs, is that we see this increase, the splitting or gap that increases when there's no superconductivity in here at all. If we do this at a higher temperature, like 10 degrees or 15 degrees, we don't see much magnetic field behavior at all, which tells you that we only see this splitting with field, which I will tell you in all cases is linear with field, either if it's in the superconducting state or the preformed or pseudogap state. And so we argue you have to have some kind of pairs. And I don't think I want to go into much detail, just to tell you that one of the models that we're using is that in these heavy ferrand materials, like I said, this one has cerium. And the F levels are at least doubly degenerate. It's called the Kramer's doublet. And Pierce Coleman and Rebecca Flint came up with this model that seems to work, but they're working on it again now, is that if you can have two electrons scatter off at the same F level, that will cause them to correlate in some way. And because and that will grow linearly with increasing applied field. So it fits the linear part. It also fits that you need to have some pairing to have this happen. It doesn't happen at 10 degrees.
Well, very interesting, very interesting. Thank you very much, Professor Greene. So I think I will stop the recording.